Hello. In the previous lecture, we defined radical extensions and polynomials that are solvable by radicals. Now, let's quickly recall the definition of both of these concepts. We say E over F is a radical extension if there is a chain of fields starting from the base to the top with the following properties: that each time we are adding some nth root of unity of one of the elements of I field to this field to get to the next step. So essentially, this is coming from the idea of solving polynomials by radicals. So when we want to solve a polynomial by radicals, each time we take the nth root or mth root, n sub ith root of one of the elements of the field that we have already produced. And the field that we have already produced means that we are using addition, multiplication, subtraction, and division from the things that we have already created in order to get a new elements inside that field. And then we possibly get another radical of this element and continue like that. If we can manage to solve a polynomial using radicals, addition, multiplication, subtraction, and division, then the solutions should belong to a field extension that's a radical extension of our base field. So that's the idea of introducing radical extensions. Okay, so now what we want to do today is to understand properties of radical extensions and therefore try to understand properties of polynomials that can be solved using radicals: addition, subtraction, multiplication, and division. Okay, so our immediate goal is first to change a radical extension by a possibly larger field extension, but gain a lot of symmetries. We have learned that the symmetries of a field extension, automorphisms of E, F automorphisms of E, is largest when E over F is a Galois extension. So that's our goal. We want to change the field extension E over F that we are given, a radical extension. We want to change it and create a Galois radical extension that contains our initial radical extension. So that is our next goal. So again, our next goal is to find an extension. Later, actually, I've changed this E prime to L. Let me change it to L. So I want to find, so given a radical extension E over F, we want to find an extension L of E such that L over F is not only radical, but also Galois. So it has enough symmetries as large as possible. Given its dimension, it's the largest number of symmetries that it can have. So that's our goal. And now we are going to do it in many steps. Actually, I've written here 2 lemmas, but then I realized that there are at least 3 of them. So we start with a few lemmas. And then some of these lemmas are actually interesting on their own, and they are not just auxiliary results to prove this theorem. But nevertheless, so we are going to start with these lemmas. So what are they? A few of them just give us a better picture, a better understanding of radical extensions. Then one of them is going to give us a better understanding of Galois extensions. And then we can combine them together in order to get a Galois radical extension. Okay, let's start with showing that if I have 2 blocks and both of them are radical, When I put them on top of each other, I get a new extension that is a radical extension. The statement is rather easy, but let's go over it. So if you remember this type of phenomena, we called block tower phenomenon. So now we are going to show this type of result for radical extensions. So suppose L over E is a radical extension, and E over F is another radical extension. We want to show that L over F is a radical extension. Let's just see what it means that it's a radical extension. When we say that L over E is a radical extension, it means that I'm giving you a sequence or a chain of subfields. Let's call them L sub 0, that's just E, starting from the base, L sub 1, and so on. But what is the property of this chain? The property is that each time I'm adding some nth root of one of the elements of L sub I to L sub I in order to get the next field. So L sub I plus 1 is nothing but L sub I joined with alpha sub I for some alpha sub I. When I raise this alpha sub I, when I raise it to some positive integer, when I look at the alpha sub I raised to power n sub I for some positive integer n sub I end up getting an element of the field L sub I. So that's the definition of radical extension. So knowing that it's a radical extension, we can get this chain of fields. Now, E over F is also a radical extension. So I can write down the same, properties, this time starting from F, the base of this field extension, and ending to the top, that is E, and fill it out by chain of fields. Again, each time the new field is generated by the old one and a zero of a polynomial of the form x to power m minus b for some b inside the smaller field and some integer m. So, okay, so far I just wrote down what it means that both of these field extensions are radical extensions. Now I'm going to simply concatenate these chains, and they start this time from F and end to L. And notice that where this chain starts, is exactly where this chain ends. So I can actually concatenate these chains. So I start from F, I get to E sub R, and then I start from L sub 0 and end to L. And as you can see, each time, but by looking at these properties over here, each time I'm adding a zero of a polynomial of the form x to power k minus some element in the previous field. So this chain actually shows us that the extension L over F is indeed a radical extension. And that's exactly what we wanted to show. So as you can see, this was a rather easy statement, but it is important to note that when I add two blocks where both of them are radical extensions, all of a sudden I get an extension that is also a radical extension. So I start with this block, I put another one, and then I get that L over F is a radical extension. Okay, so that was easy. But let's start with a lemma, and in the next lemma is going to give us a machinery of getting Galois radical extensions. So if you remember, the way that we can construct Galois extensions is via splitting field of a separable polynomial. So we are going to consider certain polynomials that for sure are going to give us Galois extensions after looking, that are going to give us radical extensions. Okay, so what is the statement? Suppose that I give you a field f, and because I don't want to concern myself with separability issues, I'm going to assume that characteristic of my field is 0. That way we know for sure every finite extension, every algebraic extension is automatically separable. So I don't need to worry about separability condition. I can just focus on normality, and that I can get for sure by looking at the splitting field of every polynomial, any polynomial. Okay, so characteristic of field is 0, and I give you m elements inside this field, a1, a2, am. Then I consider the polynomial x to power n minus a1 times x to power 2 minus a2 times x to power n minus am, and so on until I get to the mth term. And now this is clearly a polynomial inside f, and I consider this splitting field of this polynomial over the base field f. So it is automatically a Galois extension because it's a splitting field of a separable polynomial. Over a characteristic 0 field, every polynomial is separable. So this is a separable polynomial, and I'm getting that E is for sure Galva extension. So one thing that I have to mention, again, we are using this convention and that we call a polynomial separable when all of its irreducible factors do not have multiple zeros in their splitting fields. We are not assuming that the polynomial itself does not have multiple zeros. In this convention, we are allowing for the polynomial to have the same irreducible factor many times. So we even consider x minus 1 to power 5 to be a separable polynomial. This convention is very useful from Galois theory, field theory point of view, even though because it depends on the field of coefficients of the polynomial, it makes it a bit non-canonical. So that's why each time when we say separable, we have to be careful to mention that we are considering this as a polynomial inside f bracket x, and this polynomial is a separable polynomial of f bracket x, or we say it's a polynomial that is separable over f. So we have to always make sure that we mention the field of coefficients as the definition of our and the definition that we have provided for separability does depend on the choice of the field of coefficients, because we are saying all the irreducible factors. And when we say irreducible factors, I have to I have to say in what ring, and the ring that we are considering is f bracket x. So all the irreducible factors of this polynomial in f bracket x are not supposed to have multiple zeros in a splitting field of those polynomials. Okay, so because some had this question, I had to clarify this. So now let's go back to the lemma. Okay, so we are given this polynomial x to the n minus a1, x to the n minus a2, and so on, and then I'm looking at the splitting field of this polynomial, and the claim is that this splitting field gives us a field extension that is both Galois and radical. We have already explained why it is Galois. It is a splitting field of a polynomial over f, and therefore it is a normal extension. And characteristic is 0, and therefore it is also a separable extension. That's one way of saying it. Or alternatively, I can say because characteristic is 0, every polynomial is separable. So E is a splitting field of a separable polynomial, and therefore it is Galois. Therefore, the field extension that we get is Galois. Okay, so the Galois part we have already discussed. Now let's see why it's a radical extension. For that, I have to go back to see what it means that E is a splitting field. When we say E is a splitting field, it means that I can decompose the given polynomial into linear factors over E, and E is generated by the zeros of this polynomial. So this means I can decompose this, each one of the factors, in particular this factor, the next one, I can decompose all of them into linear factors. So x to the n minus a sub I can be written as x minus alpha sub I1, x minus alpha sub I2, and so on. And because the degree of this polynomial is n, and it's a monic polynomial, I get that x to the n minus a sub I is product of x minus alpha sub ij's. And moreover, the field is generated by these zeros and the base field f. So I start with the base field f and I add zeros of this polynomial. All together they generate this field E. That means that E is a splitting field of this polynomial. That's a definition of being a splitting field. Okay, so now I simply add these zeros one after another to the base field. So I start with the base field, add the first zero, then I add the next one, then I add the next one. And notice that each one of these alpha ij's, each one of them is a zero of one of these polynomials. So each one of the things that I'm adding is zero of a polynomial of this form. That's the definition of being a radical extension. Each time I'm adding nth root of some element in the previous field to get the new field. So therefore, I'm getting a radical extension. So that means that E over F is a radical extension. So this is how we are going to get a Galois radical extension. Using splitting fields of this type of polynomials can help us to get Galois radical extensions. Now, the next lemma is actually extremely important in other places as well. So let's pay attention to the next lemma and try to digest it. So what does it say? We have already seen that if I give you a tower of fields, L, if I give you a tower of fields, L over E and E over F, if I tell you that this part is normal, if this part is a normal extension, and this part is also a normal extension, we cannot necessarily deduce that L over F is a normal extension. So let's try to say it in the language of splitting fields. If I tell you that E over F, if I tell you that E over F is a splitting field of some polynomial in F bracket X, and I tell you that L over E is a splitting field of some polynomial in E bracket X. So these are equivalent to saying that L over E is a normal extension and E over F is a normal extension. From these, we cannot deduce that L over F is a normal extension. But the next lemma tells me that if I tell you L over E is a splitting field of a polynomial in F bracket X, then we can deduce that L over F is a normal extension. Okay, so let me write down again the warning. So the warning I wrote it over here, that if I tell you that L is a splitting field of a polynomial in E bracket X, that's equivalent to saying that L over E is a normal extension. This does not imply that L over F is normal. So again, here the big difference is that here I'm not assuming that this polynomial is in the base field. Over the base field, it is inside the intermediate, the coefficients of the polynomial f belong to the intermediate field, and from there I cannot deduce that L over F is a normal extension. So hopefully now you see the subtlety and importance of this lemma. So let's go into the argument and the statement. So what does this statement say? Let's assume that E over F is a finite normal extension. So it is indeed a splitting field of some polynomial that we have seen to be equivalent of being a finite normal extension. And now I give you a polynomial inside the with coefficients inside the base field, capital F, and I consider a splitting field of this guy over E. So I'm getting definitely a field extension of the top part of this field extension. So L is a splitting field of this polynomial F over E. So for sure, L over E is a normal extension, but we go further and we say, in that case, because this polynomial had coefficients inside the base field capital F, we can deduce that L over F is L over F is a normal extension. Not only L over E, but L over F is a normal extension. Okay, so that is the statement. Let's go through the proof. Again, because L is a splitting field of F over E, what does that mean? Let's try to understand what it means. It means that I can split the polynomial F into linear factors. I can write down F as a product of linear factors. Of course, it's not monic, so I have to take care of its leading coefficient as well. And then I write it as product of these linear factors, x minus alpha 1, x minus alpha 2, x minus alpha d. And alpha i's belong to the base field, belong to this splitting field. And a splitting field is generated by the base field, okay, but the base field here is the base field of a splitting field. Here I'm considering L as a splitting field of this polynomial over E. So that's why that means that when I add zeros of F to E, I can get L. So I add zeros of F, which are alpha 1 alpha d, to E, and I get the field extension L. Now, this is saying that L is a splitting field of the polynomial F. But we have another part of hypothesis which says that E over F is a finite normal extension. We have seen that being a finite normal extension is equivalent to saying that it's a splitting field of some polynomial with coefficients inside the base field. So E is a splitting field of some polynomial. We don't know what the polynomial is, but definitely there is such a polynomial, some polynomial in F bracket X, and it's a splitting field of this polynomial over the base field capital F. Again, what does that mean? This means that I can write down this polynomial. I can even make sure that this polynomial is monic. The leading coefficient does not play a role here. So I can make sure that G is monic, and then I write it as product of linear factors, x minus beta i's. And when I add beta i's to the base field capital F, I get the field E. So E is F bracket beta 1, beta 2, beta n. Okay, so E is generated by F and beta i's. L is generated by E and alpha i's. So this means that instead of this E over here, I can use this E over here. I can put it there. I can generate it using F and beta i's. So that means L is generated by F and beta i's. So these guys, beta i's give me definitely E. Then I can add alpha i's and I get the entire L. So L is generated by F, alpha i's, and beta j's. And remember, alpha i's are zeros of polynomial F, and beta i's are zeros of polynomial G. So F times G is product of these linear factors, x minus alpha i's times x minus beta j's. Of course, the leading coefficient should be there. Now here is the key property. Because F was inside F, capital F bracket X, and G we chose in a way to be in F bracket X, we deduce that both of these factors are in F bracket X, and therefore their product is also inside F bracket X. So all of a sudden, we are finding a polynomial in F bracket X, and when I take all the zeros of this polynomial and add it to the field capital F, I get the field L. That's a definition of being a splitting field. So this means that we found out that L is a splitting field of the polynomial F times G. and f times g, it's a splitting field of this polynomial, which is inside f bracket x, over the base field capital F. Because I'm adding zeros of this polynomial, which belongs to f bracket x, to the base field capital F, and end up getting the entire field capital L. And that's the definition of being a splitting field. And knowing that a field is a splitting field of some polynomial over capital F, we deduce that L over F is a finite normal extension. And that's exactly what we wanted to show. Okay, so this is a technique that we can start with some normal extension and create other normal extensions on top of this guy by considering polynomials with coefficients inside the base field and taking the splitting field of this guy over the top one. So that way I am guaranteeing that I'm getting an extension of the top guy, and at the same time it's a normal extension over the base one. We have used this type of result earlier, for instance, when we wanted to discuss normal closure of certain extensions. We had used this idea before, and it popped up in different proofs. But now we have it as a separate lemma. It's an important lemma. It's good to state it separately. Okay, so now we have all the needed tools in order to prove the result that I've mentioned earlier. Meaning, starting with a radical extension, I want to find a further extension of E that is both radical and Galois. Here again, I don't want to concern myself with separability issues. So I add the assumption that characteristic of F is 0. So E over F is a radical extension, characteristic of F is 0. And then I can find some extension of the top part and make sure that this guy is Galois over the base field. Not only Galois, but also radical, Galois and radical over the base field. Okay, so we are going to proceed by a strong induction on the degree of the field E over F. So I'm looking at the degree of the field extension E over F, and I want to use a strong induction on this number. If it is 1, then E is F, so I can just let L to be F as well. I mean, F or E, they are the same things. So then there is nothing to prove. It's easy to see that it is Galois, that they are the same field, and it is radical. So in that case, there is nothing to show. Now let's go to the strong induction step. So I want to show, what is the assumption? Let's start with the assumption, and then I want to see what we want to get to. So the assumption is that E over F is a radical extension. So E over F is a radical extension. What does that mean? It means that I can find a chain of fields, chain of intermediate fields, starting from the bottom, ending to the top. And each time I add some radical of an element in the field that I've already reached to in order to go to the next step. So F sub I plus 1 is F sub I joined with some n sub ith root of an element inside F sub I. So I'm adding a root of a polynomial of the form x to power n sub I minus a sub I, where a sub I belongs to the previous field F sub I. So that's the definition of being a radical extension. And I can assume that I have a strictly increasing chain of fields. In particular, when I look at the step right before the final step, I definitely get a field that is still radical, because every intermediate subfield in this chain is going to be a radical extension over the base field, because it satisfies the same property. So this smaller subfield is still a radical extension over the base field capital F. Now I can use strong induction hypothesis for this radical extension, because the degree of this extension is strictly less than degree of E over F. I'm allowed to use the strong induction hypothesis. And what does that tell me? It says that I can find some field extension of f sub m that is both Galois and radical over the base field capital F. So k over f is both Galois and radical, and k contains f sub m. So that is what strong induction hypothesis tells me. So that comes out of strong induction hypothesis. Okay, so now what do I want to do next? I want to go further. I want to extend k to some Galois and radical extension which contains E, which contains f sub m plus 1, which contains a zero, particular zero of x to power n sub m plus 1 minus a sub m plus 1. N sub m minus m sub m plus 1. Again, so let's actually list the properties that we are looking for. So we are looking for a field extension of k with the following properties. First of all, it should contain a copy of E. It should be a field extension of E. Second, it should be Galois and radical. Okay, so if it contains a copy of f sub m, that means that x to power n sub m minus a sub m, it should have at least one zero inside L. But we don't know which one of the zeros should be inside L. I mean, the only thing that we know is that alpha sub m is one of the zeros. So in order to be safe, we need to include all the zeros of this guy inside L. So this L needs to have all the copies of zeros of that. But at the same time, it's supposed to be a Galois extension over F. Now, when I give you a Galois extension, notice that k over f is also Galois. So any automorphism of k over f that I give you, I can extend it to some automorphism from L to L. So let's start with some theta inside this. So before I continue, in this block from here, in this block of argument, in this paragraph, what I'm doing is motivating the next step of the argument. Okay, so I'm trying to motivate why I'm going to consider certain polynomial. So this is a kind of backward engineering part. Strictly speaking, this part is not needed in the proof. I'm just motivating what I'm going to do next. So again, the goal is to construct this field extension of k that has these two properties. It contains a copy of E in it, which means I need to make sure this particular zero of x to power n sub m minus a sub m is inside the field L. And second, L over f is a Galois radical extension. Okay, let's again focus on this condition that it should contain a zero of this polynomial. We notice that we don't know which one of the zeros, so I need to include all the zeros. The next thing that I notice is that because L over f is supposed to be Galois, I need to be able, it needs to have kind of all the extensions of automorphisms of k over f in it. So any automorphism that I give you, I can extend it to an automorphism of L. And now what? I can apply it to this polynomial. L was supposed to have all the zeros of this polynomial. So if alpha is a zero of this polynomial, then theta hat of alpha should be also a zero of this polynomial. And that is x to power n sub m minus theta a sub m. So if all the zeros of x to the n sub m minus a sub m were already inside L, then all the zeros of these new polynomials should be also inside L. So all of a sudden we are saying that I need to consider the polynomial g of x, that's the product of x to power n sub m minus theta of a sub m, as theta ranges over all the f automorphisms of K, and I need to split this completely into linear factors inside L. That brings us to the polynomial G and the splitting field of this polynomial. We have to decide over what field. So again, we started with the goal that we have in mind. We need to have a copy of E inside L. That means we need to have a 0 of x to power n. I'm going to drop the indices, index m, in what I'm going to say in all these arguments, because it makes it more understandable. So we need to include at least a particular 0 of x to power n minus a inside the field L. But because we do not know which one of the zeros is going to be the one that we have inside E, I need to include all the zeros of this polynomial inside L. Okay, so that's some splitting field that we need to consider. But then we also argue, because L over F is supposed to be a Galois extension, if I start with some automorphism of K, you see, I want to change this coefficient A, and I want to use an automorphism of this Galois extension in order to change it. But when I want to do it, can I do it inside L? And the answer is yes, because L over F and K over F, both of them are supposed to be normal extensions. So any automorphism of K over F can be extended to an automorphism of L over F. So that all of a sudden we are saying that all the polynomials x to power n minus theta of A, all of them can be splitted, can be factored into degree 1 factors in over L. So that's why we end up considering the polynomial G, that's the product of x to power n minus theta of A, as theta ranges over automorphisms of K over F. Okay, so now this is the backward arguing part of the proof. Let's go to the proof. And we consider the polynomial G, that is the product of x to power n sub m minus theta of A sub m, as theta ranges over the F automorphisms of the field K. So I look at this polynomial, and the claim is that this is a polynomial in F bracket x. We have seen arguments similar to this before, where we didn't have any power, but the argument is identical to that. So we want to show that it belongs to F bracket x, and the key point is that we are going to show that it is, all the coefficients are fixed by this group. So all the coefficients belong to the fixed points of the group of F automorphisms of K. But because the extension K over F is Galva, the fixed points of the K of F automorphisms of K is precisely F. And that gives us the result. But let's go through the argument a bit slower. For every automorphism, F automorphism of K, I can apply this F automorphism to this polynomial G. So when I apply to this polynomial G, okay, because it's an automorphism, I can extend it and view it as an automorphism of the ring of polynomials K bracket X. Then I apply it to this product. When I apply to this product, what happens? When I apply this to this product, the theta term is sent to x to power n sub m. This part doesn't change, minus theta prime of theta of A sub m. Now I have to consider the product of these terms. But notice that theta prime theta ranges over the entire group of automorphisms, F automorphisms of K. I'm getting the same terms, I'm just permuting them. So when I apply theta prime to this product, then I'm just permuting the terms of the product. I'm not changing the product at all. So theta prime of G is still G, no matter what theta prime I pick from this group. That means all the coefficients of this polynomial are fixed by this group. So all the coefficients of G are fixed by this group. So all of them belong to the fixed points of this group. But notice that this is a finite Galois extension. Because it's a Galois extension, F is the fixed point of the group of F automorphisms of K. So the field of fixed points of this group is F. That's one of the equivalent properties of being a Galois extension. So K, or you can refer it to the fundamental theorem of Galva theory. In either case, we know that the set of fixed points of F automorphism of K is F, if and only if K over F is a Galois extension. Okay, so finite Galois extension is what we proved. So that means that this binomial does belong to F bracket X, and that's exactly what we wanted to show. Okay, so we have shown this claim. Let's see how we can use it. Let's L be a splitting field of this binomial over K. So again, we are in this kind of picture. We have F here, we have K on top of this, and this is a Galois extension. And now I'm considering the extension over K, but remember G belongs to the ring of binomials with coefficients inside F bracket X. So I take this, that's what this claim gives us. So G belongs to F bracket X. Now I'm considering splitting field of G over the base field capital F. And what we have proved in the previous lemma is that, where is it? It's over here. Here we showed that if I start with an extension, E over F, and I give you a polynomial, F inside F bracket X, and I consider a splitting field of this guy over E, then L over F is a normal extension. So by considering L a splitting field of G over K, because of this claim and knowing that G belongs to F bracket X, we deduce that L over F is a Galois extension. This is this part of the argument here. I go back to these two lines and tell you what that part is about. But so far I'm telling you that G belongs to F bracket X. K over F is a normal extension, it's a Galois extension, and L is a splitting field of this binomial over K, and from these we can deduce that L over F is a Galois extension. It's a normal extension, but its characteristic is 0, therefore it's a Galois extension. Okay, so this part of the argument, we are using the lemma that I have just pointed out. Now let's see how can I know that it's a radical extension. Notice that L is a splitting field of what? L is a splitting field of this binomial. L is a splitting field of this binomial over here. So it's a splitting field of product of x to power n minus some elements inside the field K. You see theta of A sub m's, all of these theta of A sub m's belong to the field K. And now I'm considering a splitting field of this binomial, and this is exactly what we have over here. Where is it? So maybe it was over here. Yes, one more page. Yes. So we had, so if I change this F to capital K, you get exactly that. So in that page, we are using it for this. So I change this to K and change this to L. Then these A sub i's are changed to theta of A sub m. So theta of A sub m's belong to K, and L is a splitting field of theta of these guys. So as theta ranges over the automorphisms of as theta. So I'm replacing this with product of x to power n sub n minus theta of a sub m's or something like this, where theta is inside automorphisms of this. So we are using this lemma for these polynomials, for this polynomial product of x to the n minus theta of a's, as theta ranges over the f automorphisms of k, and here instead of f I have to use k, and instead of e I'm going to write it as L, and we notice that theta of a sub theta of a's belong to this. So because I don't want to raise confusion, let's drop the index for now. Okay, so this is we are applying this lemma for these parameters. K, we are getting L, and instead of a sub i's, I am applying f automorphisms of k to a. So let's go back over here. Therefore, by that result, we deduce that L over k is a radical extension. We also notice that k over f is a radical extension. That's by the induction hypothesis. Now, you have two blocks. L over k is radical, k over f is radical. So I put them together. I deduce that L over k is also radical. So k over f is radical extension. Another result that we have, this kind of block tower phenomenon that we showed for radical extensions, we can deduce that L over f is a radical extension. So altogether, this part of the argument, we use the first two lemmas that we showed in order to show that it's a radical extension. And this part of the argument, we use the third lemma to show that it's a Galois extension. So altogether, we end up showing that L over f is both Galois and radical. Now, the final step is to argue why L contains a copy of E inside itself. Okay, so what is E? E is generated by f sub m and a 0 of x to power n sub m minus a sub m. But the way that we created L, we know that x to power n sub m minus a sub m completely factors into linear factors, completely decomposes into linear factors inside L. Again, why do we have this? Because this is, one of the factors. This is one of the factors of this product. When theta is identity, when this theta is identity, I get x to the n sub m minus a sub m. So this is one of the factors of G. And because G decomposes into linear factors over L, so does this binomial. Now, this minimal binomial of alpha sub m over f sub m divides this binomial. That means this one needs to have a 0 inside L. So I can find some alpha inside L that is a 0 of this binomial. Okay, why is that relevant? The point is that when I give you this binomial, I know that it is irreducible in f sub m bracket x. Now we have seen earlier that when I give you two field extensions, both of them contain a 0 of an irreducible binomial, then the extended fields are isomorphic, are f isomorphic. So when I add alpha sub m to f sub m to get E, or when I add alpha to f sub m, I'm going to get two isomorphic fields. So again, both alpha and alpha sub m, both of them are zeros of the minimal binomial of alpha sub m over f sub m. That's an irreducible binomial. From there, we can deduce that the field after joining alpha sub m to f sub m and the field after joining alpha prime to f sub m, they are f sub m isomorphic. So there is an f sub m linear isomorphism between these two rings. But remember, this field itself is indeed E. And this field is a subfield of L because we chose alpha prime inside L in a way to be, we chose it inside L, but alpha prime is inside L, and F sub M is inside K, and K is a subfield of L. So it's a subfield of L, and these two fields are isomorphic. So all of a sudden I can go from here to here and embed it into L. So I'm getting an embedding of E inside L. And remember, this embedding is F sub M linear, and F sub M contains F. So it's an F linear embedding of F linear embedding of E into L. So E can be embedded into L in a way that it can be F linearly. So I have to say can be embedded into L F linearly by an F linear map. That is important because the field extension should be embedded into the field extension of L over F. So altogether, we get this field extension of L over F that is both Galois, radical, and there is an F embedding of E into L that completes the proof of induction step. So altogether, what did you get? We said that if I start with E over F and I tell you that it's a radical extension, we can find some further extension of E, that's called it L, so that L over F is radical and Galva. So that's the content that we show. And why did we do that? Because we know when we work with Galva extensions, we have a lot of symmetries. So in a sense, we show that the number of symmetries of a field extension is always at most the degree of the field extension, and equality holds exactly when the field extension is a Galois extension. Okay, so let's see how it can help us. What was the goal? Why did we prove this theorem? Why do we care about having a lot of symmetries in our field extension? At the end of the day, we want to understand polynomials that are solvable by radicals. So that's why we studied radical extensions. Now, when I give you a polynomial and I want to study the polynomial itself, we don't care as much about these auxiliary radical extensions. We care about the polynomial and therefore about zeros of the polynomial, and that means splitting field of the polynomial. We care about the splitting field of the polynomial, and what Galois taught us is that in order to understand zeros of the polynomials, we need to focus on symmetries of zeros of the polynomials, meaning symmetries of a splitting field of the polynomial. So that's what we want to do next. We want to see, knowing that F is solvable by radicals, what can we deduce about symmetries of a splitting field of this polynomial over the base field capital F. So that's our next goal. We want to use this Galois radical extension that we have proved to exist, and use this in our advantage to study symmetries of a splitting field of a polynomial that is solvable by radicals. Okay, so let's go through the setting. So again, because I don't want to get certain complications from a separability condition, I'm going to assume that my field is a characteristic zero field. Then I start with a polynomial small f, and I assume that it is solvable by radicals. What does that mean? This means I can find some splitting field, I can find some radical extension, E, of the base field capital F, which contains an intermediate subfield that is a splitting field of the polynomial f over the base field capital F. So that means that the polynomial is solvable by radicals. That's a definition of being solvable by radicals over capital F. Now, first things first, we say, okay, by the previous theorem, without lots of generality, I can assume that my extension is not only radical, but also Galois. So more precisely, by the previous theorem, we can find some extension of E such that L over F is both Galois and radical. So without lots of generality, I can assume that this field extension is already Galois. And let's remember that when we say it's radical, it means that I have this chain of intermediate subfields with these properties that each time I'm adding a radical of one of the elements in the previous field. In the previous lecture, we actually discussed that when we have enough roots of unity, then we can make sure that at least, all these blocks, except maybe the first one, are Kummer extensions. And Kummer extensions are extremely useful because we understand that the group of isomorphisms of the Kummer extensions, all of them are cyclic. And even the first one, we understand that it's a kind of generalized cyclotomic polynomial, and therefore the group of isomorphisms of the first block would be again an abelian group. So that's what we are going to do. We are going to repeat again in this setting. So we have this Galois radical extension, and we want to extend it further and make sure that all these blocks are either Kummer extensions or cyclotomic extensions, generalized cyclotomic extension. Okay, so and we've seen that it's enough to add enough roots of unity. What roots of unity? We need to have n sub ith roots of unity for every I. So we are going to take the least common multiple of n sub i's and add that root of unity to the base field, capital F. So we let n to be the least common multiple of these n sub i's. Now I need to include the nth root of unity to the base field, and that means I need to look at the polynomial x to the n minus 1, which clearly belongs to f bracket x, and then I'm going to consider a splitting field of this guy over L. Notice that again, I have this field extension in the lemma, the third lemma that we showed. So we have F over here, we have L on top of this, which is a Galois extension, normal extension, and then we are given x to the n minus 1, which belongs to the smaller field. And now I'm considering a splitting field of this guy over the top one, and I'm kind of calling that L hat. But because this polynomial belongs to the smaller, the coefficients of the polynomial belongs to the smaller field, we can deduce that L hat is not only a normal extension over L, but it's also a normal extension over F. Okay, so, and because characteristic is 0, we deduce that L hat is because x to the n minus 1 is inside f bracket x, and L over F is a finite Galois extension, we deduce that L hat over F is a finite Galois extension. Again, the lemma tells me that it's a finite normal extension, but characteristic is 0, so we can deduce that it's a finite Galois extension. Okay, so L hat is a finite Galois extension, but at the same time, notice that it's a splitting field of the x to the n minus 1, so over L. Therefore, L hat over L is a radical extension. L hat over L is a radical extension. L over F is a radical extension. Again, I can put these blocks on top of each other. I can deduce that L hat over F is a radical extension. So L over F is radical. L hat over L is also radical. So I can use block tower phenomenon that we discussed and deduce that L hat over F is a radical extension. So it's an extension that is, so far again, Galois, radical, but now we have enough roots of unity. And therefore, all these blocks So when I add this root of unity, zeta, characteristic is 0, we have proved in the previous lecture that when characteristic is 0, then x to the n minus 1 has n distinct zeros. And from there, we deduce that there are elements that have order n inside this splitting field. And all the zeros would be powers of this zeta. So x to the n minus 1 would be product of this x minus zeta i's, zeta to power i's. And the splitting field L hat is nothing but joining zeta to L. Now we take the zeta and add it to the fields, intermediate fields that we had earlier. So these fields that come out of here, because it's a radical extension. Now we add this zeta to these fields and call them E sub i's. So f would be a subfield of E sub 0, which means f adding zeta to f, then adding zeta to f1, adding zeta to f2, and so on. But remember, fi's are created in a way that each time I'm adding a root of the polynomial of the form x to power n sub I minus a sub I. Now I'm adding the same alpha I to e sub I to get to the next one, because e sub I is just f sub I added zeta. So I'm adding zetas to these things. So e sub I plus 1 is e sub I joined with alpha I, where alpha I is one of the zeros of this binomial. As we have discussed in the previous lecture, these are Kummer extensions because e sub I does contain n sub ith root of unity. E sub I contains n sub I distinct n sub ith roots of unity, or an element of order, multiplicative order n sub I. So therefore, this is a Kummer extension. And that implies that the group of automorphism, so first of all, it's a Galois extension. And second, the group of automorphism of this extension is a cyclic group. So this is a Galois extension, and the group of automorphisms of E sub I plus 1 over E sub I is a cyclic group. Now in this chain, we understand all the blocks. How about the first block? The first block is a generalized cyclotomic polynomial, and for those cyclotomic extension, and for those ones, we have also discussed that the extension is Galva, and the group of automorphisms can be embedded into the group of units of Z sub n. In particular, it is an abelian group. So the group of automorphisms of E sub 0 over f is an abelian group. So this means that at the end of the day, I'm getting a chain of intermediate subfields where each one is a Galois extension of the previous one, and the group of automorphisms of each one of these blocks is an abelian group. So in fact, the first one is abelian, the rest are even cyclic. So what does it tell me about the group of symmetries of the entire group, or the group of symmetries of the entire field extension? And more importantly, what does it tell me about the group of symmetries of a splitting field of the polynomial f that we started with? But let's start with a group of automorphisms of L hat. When we use Galois bijection, fundamental theorem of Galva theory, Galois bijection between subgroups and intermediate subfields, having these intermediate subfields E sub i's, we get a chain of subgroups for the group of F automorphisms of L hat. So what are these subgroups? So F automorphisms of L hat contain E sub 0 automorphisms of L hat, and then I restrict it more and more. I say E sub 1 linear, E sub 2 linear, and at the end I ask E sub n plus 1 linear, but L hat is E sub n plus 1. When I say E sub n plus 1 linear, that means it's just identity. So maybe it was better if I written this as the identity, the set that has only identity element. Anyway, it's a trivial group. So we get this chain of subgroups of F automorphisms of L hat. Now let's see, when we say E sub A plus 1 over E sub I is Galois and the group of automorphisms is abelian or cyclic, what does it imply about L hat automorphisms of L hat? Again, here I'm going to use the extension. So we have L at top, L hat at top. I have E sub I plus 1 as an intermediate subfield, and then E sub I. So because L hat over F is Galois, L hat over this guy is Galois, and because this is over this guy is Galois, we can deduce that E sub I plus 1 linear maps, linear automorphisms of L hat, is a normal subgroup of E sub I linear automorphisms of L hat. So this is a normal subgroup. And moreover, when I start with an L hat automorphism, E sub I linear L hat automorphism, when I restrict it to E sub I plus 1, I get an automorphism of E sub A plus 1. And the kernel consists of E sub I linear, E sub I plus 1 linear automorphisms of L hat. So this part of an argument we've seen before again, that the quotient of L hat E sub I linear automorphisms of L hat mod out by E sub I plus 1 linear automorphisms of L hat is isomorphic to E sub I plus 1 E sub I linear automorphisms of E sub I plus 1. So this part of the argument comes from restriction map. So we start with an automorphism of L hat, and I restrict it to an automorphism to get an automorphism of E sub A plus 1. Knowing that it's a normal extension over E sub I can actually get a well-defined automorphism of E sub A plus 1. And by definition, kernel of this map is precisely this. So I can use the first isomorphism theorem for groups to get this isomorphism over here. And because E sub I plus 1 over E sub I is a Kummer extension, we deduce that this group is a cyclic group. So altogether, we get that we have this chain of subgroups, and each one is a normal subgroup inside the other one, inside the previous one. And the quotients are cyclic groups. How about the first one? The first one, again, because E sub 0 over F is a Galois extension, by a similar argument, we get that E sub 0 automorphism. Here I'm looking at this tower this time. I have F, E sub 0, and L hat over here. And this part over here is, again, Galois, and this part over here is Galois. So again, by the fundamental theorem of Galva theory, we deduce that the E sub 0 linear automorphisms of L hat is a normal subgroup of F linear automorphisms of L hat. And the quotient, by a similar argument, is isomorphic to F automorphisms of E hat, of E naught. And that one, again, is a generalized cyclotomic extension. Therefore, it's an abelian group. It is, in fact, a subgroup of the group of units of Z sub n. So altogether, we say that if I call the F automorphisms of L hat, if I call it G, and E sub I automorphisms of L hat, if I call those guys G sub I, this means that G has this chain of subgroups. Each one is normal in the larger one. So G sub I plus 1 is a normal subgroup of G sub I. And the quotients of G by G naught, that's over here, G naught by G1, G1 by G2, and GM by the identity one, again, part of this. All of these quotients are abelian groups. This is a special property of the group G. Not every group have this kind of property. Because we were talking about solving polynomials, and we reached to this property for groups, we say a group is solvable if it has this property. And we will see that it's quite a special property for a group to have. So this was about L hat, but remember, we want to understand symmetries of a splitting field of a polynomial that is solvable by radicals. So we need to go back to a splitting field of the polynomial f. So all these things were about understanding a splitting field of the polynomial f. So you want to use these auxiliary information and get back to that. But what does it mean that K is an intermediate subfield of this guy and K over F is a normal extension? Again, the picture is this time it is like this. I have F, I have this intermediate subfield, and I have L hat over here. And I know that K over F is Galois and L hat over F is Galva. So again, similar as the part of the argument that we have already. If I look at the K linear automorphisms of L hat and call that guy N, then N is a normal subgroup of F linear automorphisms of L hat, and that one we denoted by G. And remember, again, by a similar restriction argument, G over N is isomorphic to F linear automorphisms of K. So this is a group that we care about. This is symmetries of a splitting field of the polynomial f. This is a group that we care about, and we just discussed that this is isomorphic to G over N, where G is this solvable group. G has this chain of subgroups where each one modeled by the next one is an abelian group. Now we want to pass this property to G over N. That is what we are going to do next. So we are going to take those G sub i's and mod them out by N. So this means that I'm taking this natural quotient map from G to G over N. That's just the natural quotient map that sends every element to the coset that's represented by that element. And then I apply this group homomorphism to each one of these subgroups G sub I. So when I apply to the entire group, I get G over N. That I know to be isomorphic with F automorphisms of K. Then when I apply it to these subgroups, each one is normal in the next one. And that means that I'm getting a chain of subgroups where the I plus 1 is a normal subgroup of I. So I'm getting a chain of decreasing sequence. I'm getting a decreasing sequence of subgroups, and the next one is a normal subgroup of the previous one. Now I want to argue that this chain also has this property that each one modeled by the next one is an abelian group. And therefore, as I've mentioned, this property, we say that the group is solvable. Therefore, we want to deduce that the group of F automorphisms of a splitting field of a polynomial that is solvable by radicals is a solvable group. Okay, so again, that means I want to show that this chain of decreasing, this sequence of decreasing subgroups, each one divided by the next one is an abelian group. What does that mean? This means that when I pick two elements inside this quotient, I end up, when I multiply them, I can change the order of multiplication, and I end up getting the same element. So that means when I multiply inverse of one of the coset representatives by the other one, I end up getting an element inside the subgroup. So again, let's recall that when I tell you an element G1 times N is the same as G2 times N, this happens if and only if G1 inverse G2 is inside N. So this is a type of result that maybe I should not say N, let's call it H. So this is a type of result that we are using over here. So when I want to show that these two cosets are the same, I need to multiply, I'm going to multiply inverse of this guy by this, and I need to say that this belongs to this subgroup. Inverse of this guy is P sub n, so P sub n G inverse, but then I multiply by this. So P sub n G prime inverse, so inverse of this one times inverse of this, times this, times this. It should belong to the subgroup. So this is equivalent to saying that if this star holds for every pair G and G prime, that's equivalent to saying that the quotient is an abelian group. But remember, P sub n is a group homomorphism. So therefore, this star over here holds exactly when I can pull out these pn's, and in this element over here is P sub n of G prime inverse times G inverse times G prime times G. So I need to show that this element belongs to P sub n of G sub I plus 1. Again, P sub n is here, it's in fact a function, so it's enough to show that this element belongs to G sub I plus 1. But what is my hypothesis? I do know that G sub I over G sub I plus 1 is an abelian group. So I can repeat this argument this time using cosets G that are represented by G and G prime modeled by G sub I plus 1. Because this quotient is abelian, we do know that we have this equality from which I can deduce the desired claim. So this element, G prime inverse times G inverse times G prime times G, does belong to the subgroup capital G sub I plus 1. And that's exactly what we wanted to show. And that completes proof of this claim. So altogether, what did I end up getting? We end up getting that the group of F automorphisms of K has a chain of subgroups starting from G, getting to the trivial subgroup. And each time that I look at the n sub I and mod it out by the next one, I get an abelian group. Such a group we call to be solvable. So if I have a group G, we call it solvable if I do have this chain of subgroups with this property. And what we have proved altogether is this result that's due to Galois. So we say it's a theorem of Galois about solvability of polynomials by radicals. And it says that if F is a field of characteristic 0, and I give you a polynomial in F bracket X, I look at a splitting field of this polynomial over capital F, then if F is solvable by radicals over capital F, then the group of F automorphisms of this splitting field is a solvable group. So not every polynomial can be solvable by radicals. If I give you a polynomial that is solvable by radicals, then the group of symmetries of the field extension that comes from the splitting field should be a solvable group. Okay, so at this stage, you might ask, is it a real restriction? Do we have any group that is not solvable? That's a legitimate question. We will discuss it further in the next lecture. We will discuss using a result from group theory that you've seen earlier, that alternating group is a non-abelian simple group as soon as n is at least 5. We use this result from group theory and discuss and show that alternating group and symmetric group are not solvable if n is at least 5. Then we also argue that in certain cases for some polynomials f, the group of symmetries the group of automorphisms of their splitting field is isomorphic to S sub n or A sub n, from which we deduce that these polynomials cannot be solvable by radicals over the base field. In fact, we argue certain polynomials in Q bracket X, certain polynomials of degree 5 in Q bracket X have this property that their group of symmetries is going to be isomorphic to S sub 5, which is not a solvable group, from which we deduce that there are degree 5 polynomials that are not solvable by radicals. So we will continue in the next lecture.